It's time to look at carbocation rearrangements a little more deeply than we did previously. Sometimes in addition reactions, we observe rearrangement of the carbon skeleton. And an example of that is here with this electrophilic addition of hydrogen chloride to this alkene. And if you look at the products, the minor product, notice the percentages here, has the same carbon backbone, 4 carbons, 2 methyl groups here on this carbon, as the starting material, but the other carbon, the other compound, the carbon backbone is rearranged, and you'll notice that we do have the 4 carbons, but we have a methyl group on carbons 2 and 3 in this structure, and it's in fact the major product of the reaction. So how does this come about? So to rationalize this, we need to consider the mechanism. Typically, these reactions will begin with the usual protonation of the double bond, and we would expect that protonation to be regioselective in a Markovnikov sense, producing a more stable carbocation. In this case, a secondary carbocation is formed in preference to the primary, and that this wouldn't happen at all. But that hasn't changed the carbon backbone. It just gives us a secondary carbocation, and we've seen those carbocations as viable intermediates in reactions before. So how does this major product come about? So as is typical, these sorts of structures, when they can rearrange by simple shifts of hydride or alkyl groups, they would do so incredibly fast, and I can't emphasize that enough. So let's now think about what can happen to that secondary carbocation. So this is the same one depicted on the previous slide. One thing that can happen is the intermolecular reaction between the chloride ion and the carbocation, and that leads to the minor product. So that's an easy rationalization of where that comes from. So how do we get to the major product? And the answer is a hydride shift. So if this hydrogen, along with its pair of electrons, this is why it's called a hydride shift. It's effectively moving H minus because the electron pair go with it. If that shifts to this carbon, and we've seen previously how the orbital alignment can allow that to happen, then that shift generates a much more stable tertiary carbocation. If chloride then adds to this, there's our major product. So why do we produce so much more of the major product if this has to happen before you can get to here? And the answer is that this intramolecular hydride shift is much, much faster than the intermolecular interaction between the chloride ion and the carbocation. The intermolecular reaction requires that the two molecules bump into one another with the right geometry in order for that to occur. That's not necessary for the intramolecular rearrangement. So these intramolecular rearrangements can be much, much faster than the encounter between two species in solution, for instance. And so because this is so rapid, you're generating tertiary carbocation very, very quickly, and then the carbocation is reacting and producing these major products. It's a very common observation. In a broader sense, these rearrangements are often referred to after the pioneering German chemists Wagner and Meerwein, who studied these. And so whenever hydride or even alkyl groups shift, we call them Wagner-Meerwein rearrangements. So here's a similar reaction. This is a slightly different substrate. So compared to what we saw on the previous slide, we now have a methyl group here in this position. And again, we can kind of think about mechanistically the electrophilic addition occurring. This one begins just like the previous one, so we're going to get a Markovnikov addition of hydrogen, producing initially a secondary carbocation. But in this case, we can get an alkyl shift, so a methyl group moves over in the same fashion. So this is essentially a methyl anion shift, and again produces a tertiary carbocation. This is an intramolecular process, the alkyl shift, so it's much more rapid than the intermolecular interaction between chloride ion and carbocation. And so we generate a significant concentration of the tertiary carbocation, and its reaction leads to the major product. And you notice the product distribution here depending on the specific reaction condition, somewhere between 25 and 40% of the unrearranged product, but 60 to 75%. So in general, carbocations will rearrange if they can produce more stable carbocations, and they will do so quite rapidly, so that we often see the major products produced from the rearranged carbocation. There's a concerted variation on such rearrangements that avoids the formation of a primary carbocation. So if you look at the reaction of neopentyl iodide with water in the presence of a silver salt of some sort, you get SN1 reaction, and you produce exclusively 2-methyl-2-butanol. And so you kind of have to ask the question, how does that come about? Now, this is not an electrophilic addition, but rather an SN1 reaction. So the initial step of the reaction needs to be ionization of the iodide. Now, you could draw ionization of iodide to produce this carbocation, but that's primary carbocation, which are typically energetically unavailable. So how do you get around this mechanistic pathway that invokes the formation of a primary carbocation? And the answer is that the alkyl shift can happen at the same time as ionization, so that these two are happening in a concerted fashion. And so the alkyl shift moves as the iodine is leaving, and we go directly to the tertiary carbocation. And so essentially this mechanism is not operating, and the reaction is happening by this concerted process where the rearrangement accompanies ionization, and then we get the rearranged product exclusively. And again, the rearrangement, this whole process is intramolecular and can be quite rapid and energetically favorable over this very unstable primary carbocation. It's important to note that rearrangements can only occur if you have orbital alignment. So hydride shifts onto carbocations only happen when the sigma bond interacts with the carbocation. So that's the same interaction we invoke to explain hyperconjugation allows for the hydride to shift over in the formation of a more stable carbocation. So it's in this case a sigma CH bond interacting with a 2p orbital. The shift can occur. If the orbitals cannot align, if you have, for instance, a bicyclic compound where the geometry is constrained, where this sigma bond, for instance, cannot align with the empty p orbital, then you don't observe rearrangement. And so there are some examples of that. Let's look at a couple other instances of how carbocation rearrangements can play out in interesting ways. In this example, starting here with the compound in the gray box, we have a cyclobutane ring attached to this tertiary alcohol, and a couple different reactions can occur. One is if you just treat this compound with HBr, you end up producing this bromide, and clearly something has gone on. This carbon backbone isn't anything like what we started with. Likewise, if you treat it with water and an acid catalyst, you get exclusively these products where you've got these cyclopentane and pentene rings in them. So what in the world is going on here? Well, in each case, these are acids, HBr, H2SO4, and so in both cases, we can get protonation of the hydroxyl group to form an oxonium ion, and then that allows ionization to occur to form a carbocation. And so the initially formed tertiary carbocation looks perfectly fine. It's a tertiary carbocation, but this adjacent ring is a strained ring. That's a 4-membered ring. Remember, 4 and 3-membered rings in particular are quite strained. And if orbital alignment allows, and it can happen here, then one of these carbon-carbon sigma bonds can migrate over to that carbocation. That would leave this position as the positive charge. And that process, even though it leads to a secondary carbocation, relieves the ring strain. And so even though we're going from a tertiary to a secondary carbocation, the energy, um, the potential energy of the system decreases because we've relieved so much ring strain, and we go to the five-membered ring. We can draw that slightly differently like this. It's just simply this dimethyl cyclopentyl cation. And then from there, the reaction can proceed in the usual way, where we can either get SN1 substitution after water adds and is deprotonated, or we can get an E1 sort of reaction that occurs, but occurs after an additional rearrangement. We can get a methyl shift in this compound, producing a tertiary carbocation, and that tertiary carbocation can be deprotonated to give that alkene. So as an exercise for you, I'd like you to draw out the mechanism of these two processes, starting with this carbocation in particular, this methyl shift and then deprotonation to lead to that alkene. So the previous example was a ring expansion where we were leaving strain in a very small strained ring and producing a less strained larger ring. There are also examples where you find ring contraction is favorable. And this is one of those. So if we look here at the top of the slide, our reaction is the one you see here. So this is a diol, has two alcohols in the molecule, just treated with aqueous water or acidic water. And a couple things happen. You can notice that in each one we have a carbon backbone rearrangement. In this case, the methyl groups are on adjacent carbons, they end up on the same carbon. In the other case, the 8-membered ring becomes a 7-membered ring. So what in the world is going on in this? And so if we look at this and think about it mechanistically, the reaction would certainly begin by protonating one of these two hydroxyls. It's a symmetrical compound, so it doesn't matter which one we protonate. And loss of water would lead to a carbocation. And that carbocation can undergo alkyl shifts in two different ways. One manner in which the alkyl shift can occur where we have a methyl group shift over, and so we end up with the two methyls on the same carbon, and we end up with our carbocation here adjacent to the hydroxyl. And if you think about the resonance forms of this, we've talked about these sorts of resonance stabilizations of carbocations before, it leads to this structure. And if that's just deprotonated, it becomes the ketone that you see there. But the other pathway is, rather than the alkyl group being the methyl group, the alkyl group could be this bond in the ring that shifts over. So drawn in this fashion, you can see that that bond moved from here to there. And so now we have a bond here. And now we have this positive charge here next to this hydroxyl group. And again, you can draw a resonance structure showing the stabilization of that cation by the oxygen, and deprotonation of this leads to the other one. This sort of reaction of these 1,2 diols, where we have these hydroxyls on adjacent carbons, is so common it has a name. It's known as the pinnacle rearrangement. The name comes from the parent compound that was studied that gave rise to these rearrangements. Previously, we've looked at this reaction, and it's worth revisiting. And this is just the acid-catalyzed hydration of alkenes. Water will add to alkenes and give alcohols under conditions of acid catalysis. We learned previously that this reaction, like hydrohalogenation, follows Markovnikov regiochemistry through the most stable carbocation intermediate. And it only requires a catalytic amount of acid. So in these example reactions, the sulfuric acid used here is just a catalytic amount, but you do need stoichiometric amounts of water for these reactions to occur. We've drawn this mechanism previously. It's worth revisiting. Like hydrohalogenation, the reaction begins by protonation of the alkene. In a Markovnikov sense, hydrogen adds to the carbon with the most hydrogens. This produces the most stable carbocation. Water acts as a nucleophile, adds to the carbocation, produces this oxonium ion. Water can then deprotonate the oxonium ion, producing our alcohol product. And you'll notice very importantly, regenerating our catalyst. So it's really fundamentally important that this is, in fact, a catalyzed reaction. So when we draw mechanisms of catalyzed reactions, we should be able to account in our mechanism for why the catalyst is not consumed in the overall process. So here, H3O plus is our catalytic species. It's what protonates the alkene, leads to the carbocation. Addition of water leads to an oxonium ion. Deprotonation regenerates the catalyst. So catalyst here, catalyst is reformed. And you can see why we only need a small amount of sulfuric acid, because every time this process occurs, regenerates the catalyst and can continue to react. So now let's expand on our electrophilic addition reactions and look at some others that take place. In industry, this turns out to be quite an important reaction, and that's the addition of sulfuric acid to alkenes. Now in this case, this is neat sulfuric acid. Neat means no solvent. So this is H2SO4 with no water present. And that's important for the overall result here. And in the absence of water, sulfuric acid will actually do an electrophilic addition reaction so that you form hydrogen sulfates. These compounds are generically known as hydrogen sulfates. Like water, the reaction follows Markovnikov-Regio chemistry. Hydrogen will add to the carbon with the most hydrogens, if you look at this first example, and the hydrogen sulfate group will add to the more substituted carbon. Now, why are these used in industry? And it turns out it has to do with engineering efficiency. If you want to convert cyclohexene into cyclohexanol, you could, in principle, use the previous reaction where you have some water and a catalyst. But it turns out there are complications to that happen on large scale. And so on large scale, they do this in a stepwise fashion where they form the hydrogen sulfate derivative, and then they can hydrolyze that hydrogen sulfate derivative using steam, essentially. And so it's just a matter of engineering efficiency on a very, very large scale. The mechanism is very simple. Remember, there's no water present, so our acid is in fact H2SO4. It will protonate the alkene. You will get Markovnikov-Regio chemistry to produce the most stable carbocation. And then in the absence of water, sulfuric acid can act as a nucleophile and add, and that produces the final hydrogen sulfate. So very simple reaction overall. Now is where it gets a little complicated. So if you're somewhere in between having water and a little bit of catalytic acid and having pure sulfuric acid, if you're somewhere in the middle, we often find that we get reactions where the alkene reacts with the carbocations that are produced in the reaction. And the simplest scenario is the one shown here, where we start with an alkene. We're using some sulfuric acid and water, and some of the products would be alcohol, some of the products would be hydrogen sulfates, but a lot of the products are the structures that we see here. And these are known as dimers. If you look at the structures of these, they're essentially two of these molecules combined in some way. Di means two, and the mer refers to units, 2 units. So they're combinations of 2 units and that kind of thing. So we're going to talk about how these form and then how you can extend the process and make plastic by polymerization. So let's look at how these reactions can occur. So if we have our alkene, so this is from the previous slide, this is our 2-methyl propene, and we treat that with Bronsted acid, it can be protonated and form a very stable tertiary carbocation. If the concentration of water is very low, but the concentration of alkene is very high, then the most prevalent nucleophile would be more alkene rather than water. So we keep our water concentration to a very minimum. So once the carbocation forms, alkene can act as nucleophile and our carbocations act as Lewis acid. And that would result in the formation of the dimeric carbocation. So we're going from one intermediate to now another intermediate. We've made a carbon-carbon bond. So the important thing here is carbocations are strong Lewis acids. Alkenes, of course, are strong Lewis bases, or good Lewis bases. They're nucleophilic. So you can see how these kind of come together. And then if we deprotonate this, we would essentially have sort of an E1 elimination reaction. And so deprotonation can happen beta to the carbocation. This is a mechanism we learned earlier. So the E1 mechanism, once you form the carbocation, if you deprotonate on one of the beta carbons, we can deprotonate here, we can deprotonate over here. Water is probably the strongest Bronsted base in these systems and would be the base that deprotonates them. And you can see we lead to these two alkene products and probably would produce the more substituted alkene preferentially. And that's how the dimers are formed in those reactions. But what's curious is these reactions often don't stop at the dimer, that they will continue to form carbocations that will continue to react with alkenes rather than get deprotonated or otherwise. So you can imagine this extending this. So here's that first step. We formed our carbocation, alkene reacts with it, forms a new carbocation, but another alkene can react and form another carbocation, and another alkene can react and form another carbocation, and so on. And you can see that the whole thing grows. That process is called polymerization. Poly simply means many units, many units. Which brings us to polymers in general. They are large molecules composed of many smaller repeating units. The repeating units are called monomers, the individual units. The names of these polymers typically are derived from the starting material. So if you polymerize ethylene, you get polyethylene. If you polymerize propylene, you get polypropylene. This is a generic structure for polypropylene. If you polymerize styrene, you get polystyrene, and so on. Alkenes generally undergo this sort of addition polymerization, and you can form all sorts of different kinds of plastics this way. Now, how long are these chains? Well, they're quite long, actually. So a typical polymer chain with repeating units, this is a propylene, and we'll look at that more closely. The number of these repeating units within the long chain can be hundreds, if not thousands of units long. So this leads to a whole world of different kinds of plastics. They have different properties depending on their molecular structure. And some of these you're familiar with, some are a little less common. So for instance, when ethylene is polymerized, you get polyethylene. It's used in packaging materials, plastic squeeze bottles. It comes in different forms, so-called high-density polyethylene and low-density polyethylene, and that just refers to how stiff the material is. When propylene is polymerized, you get polypropylene. It's used for everything from carpets to automobile tires to plastic luggage. When styrene is polymerized, you get polystyrene. Think red cups on Eaton Street or styrofoam. It's used for many other things. When vinyl chloride is polymerized, you get PVC. It's often used as kind of a replacement for leather, but it's also used for plumbing pipes. Those white drain pipes that you see in construction are typically made out of vinyl chloride. Polyacrylonitrile is a wool substitute. Think acrylic fiber, that's what that refers to. 1,1-dichloroethylene when polymerized gives us saran wrap, packaging wrap. 2-methylpropene when polymerized gives isobutyl, or what's called butyl rubber, synthetic rubber. Tetrafluoroethylene when polymerized gives us Teflon, polytetrafluoroethylene, non-stick material. And then there's some pretty complex ones here. If you take methyl methacrylate, you get plexiglass. So it's a transparent plastic, rather rigid. 2-methyl-1,3-butadiene polymerizes, gives polyisoprene. Think synthetic rubber that you would make, say, wetsuits and those sorts of things out of. So let's think about this from a reaction point of view. So we can draw that reaction generically. We've got some sort of alkenes, got substitutions on it. We need an acid catalyst to get things started, and it polymerizes. Now, This is an oversimplification of how one carries this out. It's a big problem for engineers to figure out how to make these reactions occur efficiently so that you're making quality polymer that has the right properties. But from an organic chemist point of view and looking at the chemistry at the molecular level, this is the overall process. You have many, many units. N is a large number. The acid catalysts can be a wide range of things, can be protic acids, can be Lewis acids, those sorts of things. So if you take isobutylene and you polymerize it, this would be kind of the generic structure for polyisobutylene. If you take styrene, remember pH is a benzene ring, treat that with a Lewis acid, you can make polystyrene of different forms, that sort of thing. So what does a mechanism, how would you draw a mechanism for this sort of thing? And here's an example of that. So in this mechanism, we would protonate the double bond with some sort of acid. For simplicity's sake here, I'm using just a protic acid. We protonate the double bond to form a carbocation, and then we get a series of reactions of alkene reacting with carbocation, alkene reacting with carbocation, in each case producing a new carbocation as the chain grows longer and longer. And so it happens over and over and over. You get a very long chain where N is a big number, and then something has to terminate the process. And typically that final termination is a deprotonation. Something acts as a base in the system, so it could be a hydrogen sulfate ion, for instance. If there's a little water, water is a strong enough Bronsted base to deprotonate a carbocation. And at the end of the chain, you have a double bond.